functions would really be complete without saying how they relate to differential equations in some sense. You know, the fact that you can characterize a harmonic function classically as a solution to a Laplace equation, that the Laplacian is 0. And this brings much more structure to the theory when you have the notion of a Laplacian operator and allows you to sort of solve differential equations and phrase many problems as sort of Dirichlet type problems as some kind of differential equation that you're trying to solve, and these harmonic and subharmonic functions come up as solutions to certain equations. So anyway, I want to try to mimic that theory now on p-adically. And this has the advantage you can then talk about Green's functions as the solutions to certain differential equations, and Green's functions are used in arithmetic geometry at the Archimedean places, and we'll see that, well, we won't exactly see, but they come up p-adically as solutions to, as Green's functions, as solutions to differential equations as well, but you have to use the kind of formalism that I'm going to introduce now. So the main question is, how can you define some kind of differential operator that's like this one? So classically you have, so for just certain sign convention reasons, I will take the classical Laplacian to be sort of minus d squared f dx squared plus d squared f dy squared dx dy, thought of as a two-form or as a measure or as a distribution. There's various ways you can imagine this, but I'll sort of be thinking of the Laplacian as taking functions to measures. So if you like, this is the Laplacian as a measure, and I put the minus sign in to make it kind of a positive definite operator in some sense. So, so we want to mimic this operator, but we have this wildly branched tree, and it's not immediately clear how to do it, except I gave a big hint in the last lecture, or second lecture, which was described the Berkovich projective line as an inverse limit of finite trees. And on a finite tree, or even more generally, just on any finite graph, there's a nice notion of a Laplacian just coming from graph theory. I mean, I mentioned what a harmonic function was. The value at the center is the average of the neighboring values. And there's an operator that encodes that. And I mean, in combinatorial graph theory, there's just some matrix called the Laplacian matrix. But you can sort of extend this to an operator first on piecewise linear functions, which is really the same data because you can interpolate piecewise linear functions. They're determined by combinatorial data. But then you can extend that to not just piecewise linear functions, but more general functions, such as C2 differentiable functions. And then there's a Laplacian on a finite graph, which is some kind of hybrid of this Laplacian involving second derivatives, and the combinatorial Laplacian, which encodes combinatorial information about the graph. So there's some sort of hybrid operator on a finite graph, which I'll describe in a moment. And then it's compatible with taking these inverse limits. So you can sort of compute on a bigger graph and then retract to a smaller graph and do the computation in two ways, and you get the same answer. And that compatibility property of this classical Laplacian on a finite graph will mean that you can pass to the inverse limit and get a differential operator on this Berkovich space. So that's what I'm going to do. I mean, it's a bit technical somehow, but the idea is quite clear, I think. So hopefully I won't bore you or lose you with the technicalities of it. So we'll construct via limiting process from the Laplacian on a finite R tree. Now for curves of higher genus, as I mentioned briefly, I showed you a picture of a tree that is not simply connected, which you should always keep in mind that we have to deal with such things. And the associated Berkovich space is no longer simply connected for curves of higher genus. And so if we wanted to construct a Laplacian there, we shouldn't really just look at trees, but metrized graphs. So instead of R trees, we'll look at graphs where the edges are thought of as line segments having definite lengths. These are often called metric graphs in the literature, but Rumley introduced the term metrized graphs, and we use so many results from his previous papers that it's, I just stick with this term metrized graph, but it means the same thing. Inverse limit of metrized graphs satisfying certain axioms, such as the transition maps are all surjective retractions, will be called an arboretum. but it's a little more than that. And see, arboretum, because in fact, will require that there's kind of only finitely much homology, like that circle for the Tate elliptic curve. We had a circle, and the whole space was just trees attached to that circle, right? So we had a circle, we had a bunch of trees growing out of that. So we had this whole family of trees parametrized by this circle. And I'm going to call such an object an arboretum. And by defining the Laplacian on an arboretum, well, it's more abstract. It'll be some more axiomatic thing rather than something extremely concrete. But we'll have the advantage that it will give us a Laplacian operator on any Berkovich curve, and also on M of z, which also you can think of as an arboretum. And so on various spaces that we've talked about, this formal construction will allow us to proceed. All right, so first let me set the same terminology as always, that my ground field will be algebraically closed in order to have this nice topological description. And by a measure on a space X, I will always mean a bounded signed radon measure on X. So, I mean, it doesn't, I mean, you don't have to remember that much measure theory. Just, these are allowed to be signed measures, but the positive and negative parts should be bounded. And, you know, just think of Borel measures, it's fine. So intuitively, a metrized graph is a finite graph whose edges are thought of as line segments having a well-defined length. So I said that already. A metrized graph is a compact metric space. And if it has no cycles in it, then this is the same thing as what I was calling a R tree, but I'm requiring that they be sort of finite. So a compact R tree. So metrized graph for this talk will mean a finite metrized graph. Okay, so tangent directions, this is quite familiar from what I've already said. It's just the same definition I've given before. The set of tangent directions at a point on this finite graph is just the set of equivalence classes of paths emanating from P in the graph. So no surprises there. And I was trying to find better, simpler terminology here, but for each tangent vector, I mean, it's an equivalence class of paths, but we just think of some formal unit vector as representing this tangent direction. And then instead of a path gamma of t, I can sort of think of it as p plus t times this formal unit vector for t in some interval. And in this way, I can define the directional derivative of a function f. Oh, where did the pointer go? There we go. Derivative of f in the direction v evaluated at p is just the obvious thing. So you just take, anyway, it's the directional derivative. So CPA of gamma, I think I introduced this notation CPA in the context of Berkovich space before, but so CPA of gamma would be these continuous piecewise affine functions on gamma. So real valued functions which sort of along each edge have the form AT plus B. But notice that a metrized graph has no preferred vertices and no preferred edges, really. I mean, you can, for example, the circle is a metrized graph, a circle of some length, log absolute value 1 over q or something. A circle with a given length is a metrized graph, and I mean, there's no edges. But you can choose a model. You can sort of pick some vertices and then draw edges between them and think of it as being induced by that combinatorial model. So in that sense, I allow breaks in these piecewise linear functions anywhere, at arbitrary vertices, anywhere on the graph. So there should be just some finite set of vertices that you can pick out and then draw edges between them, and then it's going to be affine on each of those edges. That's what I mean by CPA. And then for such functions, the directional derivatives are all well defined. And so we can write that the Laplacian of f, if f is a piecewise affine function, we can take, it's just going to be a sum of point masses. So in general, the Laplacian of a function that's not necessarily affine will be some measure that's not necessarily discrete. But for affine functions, this associated Laplacian will just be a sum of point masses, some discrete measure. And the mass of delta p, so the mass at the point P, will be minus the sum of the slopes in all directions leading away from P. So it's the thing we've seen before in some related context, that you look at the change in F in all directions leading away from P, and you add those up, and you take this minus sign again because of some convention that I'm following, and that's the mass at P. All right, so this is really a very simple thing, and it's completely equivalent to the usual combinatorial Laplacian, which is why I have the minus sign, because somehow if you think of piecewise affine functions as just being combinatorial things given by their values at the vertices via interpolation, then you can literally just identify this measure valued thing here with some matrix, and that's the usual Laplacian in graph theory. Right, so we're not really doing anything new other than using some fancy terminology for very classical things, but here's some properties of this Laplacian on these piecewise affine functions. So first of all, Laplacian is 0 if and only if f is constant. The Laplacians of two functions agree if and only if they differ by a constant. That follows from 1 plus linearity. Here's a kind of maximum modulus principle for graphs. If you have a non-constant function, then it will achieve, these are linear functions, remember, piecewise linear. F achieves its maximum at a point where the Laplacian is strictly positive and its minimum at a point where the Laplacian is strictly negative. So if you like, this is like the second derivative test in calculus, but for graphs. And the Laplacian is a self-adjoint operator in this sense. Laplacian of the integral of f against the Laplacian of g, that's just a finite sum, right? Because this Laplacian I define as a discrete measure. So is the same as the integral of g against the Laplacian of f. And once you take some inverse limits and Berkovichify all this kind of stuff, this sort of relation turns into something like the Weil reciprocity law. I'll leave that, something for you to think about. But anyway, there's some interesting geometric interpretation of what this self-adjointness of the Laplacian is supposed to mean. But anyway, it's, the way I've defined it, it's a self-adjoint operator. And the total mass of this measure is 0. So this is a simple but nice exercise that if you take this sum of the slopes at all points, and you add all those up over all points, you always get 0. So this is... well, combinatorially, this is just the statement that this Laplacian matrix, every row and column, it's a symmetric matrix, that's like number 4, and self-adjoint. And then this is saying that every row and column sum to 0. So this is just kind of linear algebra here. But this Laplacian extends to a much larger space of functions than just the piecewise linear functions, which is quite useful because, I mean, many interesting examples of functions are piecewise linear, like log absolute value of a meromorphic function on Berkovich space will actually be piecewise affine, will be in CPA. But something like a local height function is some limit of those guys. So like a local height on an elliptic curve is not going to be piecewise linear. It'll be some kind of limit of piecewise linear things, which in the limit, you want to be able to take the Laplacian of that and say you get some measure that's not necessarily discrete. It'd be some limit of discrete measures. So in order for applications, it's quite important to have a much larger class of functions. And the way you can think about this is, for example, this classical Laplacian is defined, that definition I gave as d squared f dx squared plus d squared f dy squared. That's just defined for C2 functions. But you can extend it to functions that aren't necessarily C2 by using distribution theory. And this sort of self-adjointness allows you to integrate test functions. You can integrate against smooth test functions and move the Laplacian over. And so in this way, you can define the Laplacian on a much larger class of functions. And this is very useful in classical analysis. So we want to do something similar. But I want to actually get measures, not just distributions. So there will be some boundedness requirements throughout. And this Rumley's idea for doing this is to use this thing he had observed many years earlier, which is something called the mass formula. And this will have an interpretation later in terms of p-adic analysis. Somehow this is encoding things like Newton polygons. So let me tell you what the mass, but this is just something about graphs still, finite graphs. So what is the mass formula? If I take a subset S, which is in the Boolean algebra generated by the connected open set, so it could be kind of some finite union of half-closed, half-open intervals or something like that. And the boundary of S is the points that belong to the closures of S and its complement, the usual relative boundary inside of gamma. And so if I have a point in the boundary, I have a set of inward pointing tangent directions and a set of outward pointing tangent directions. Because, I mean, my thing is a union of intervals. So there's certain preferred tangent directions which go into my set S and ones that go outside. So that's what in and out denote. And yeah, so I think this is clear. I mean, if P is, for example, a point, which is allowed in my definition, then there's no inward pointing tangent vectors. Everything points outward. Okay, so here's the mass formula. I mean, this is a very elementary thing, but it's rather important property of this Laplacian. So this measure, which I'll call mu, satisfies the following properties. If you have a finite union of connected closed sets, then the mass, I mean, it's a measure, right? So we can take the mass of some set E like this, some Borel set. The mass of E it's a sum over all boundary points of E, and then a sum over all outward pointing tangent vectors of the change in slopes. And there's this minus sign here. Of the directional derivatives. So you sum the directional derivatives over all outward pointing directions, and you sum over all boundary points. This is easy to prove, but it's somehow not the definition, not directly the definition that I gave. Before I was summing over all points and all tangent directions, and I was giving you the sort of a formula for the measure globally, but this is kind of saying what it does to certain special sets, that there's some interesting structure. So this is a simple exercise, but it's useful that these formulas exist. For finite union of connected open sets, I mean, roughly that's just the complement of the previous situation, and so now you have the sum over inward pointing tangent vectors of all of the inward pointing slopes at all boundary points. Now, okay, so the nice thing about this is this kind of determines the measure. I mean, these things generate the topology, and this is a regular measure. So the measure mu is actually determined by these formulas. And so what we want to do is define a Laplacian in general to be kind of any measure that satisfies these formulas. And then we can weaken. You see here we only require somehow the existence of these. Well, f doesn't have to be linear. We just have to have directional derivatives existing. But for this kind of formula, it doesn't matter if f is affine or not. As long as directional derivatives exist, you can at least talk about these kind of things. It may or may not extend to a measure on the whole space. So that's where this BDV comes in. This stands for bounded differential variation, because there's some way you can interpret this as saying that the function doesn't vary too wildly. The derivative isn't changing too wildly. So a function has bounded differential variation in this sense if, first of all, it's continuous. Second, all directional derivatives exist in all directions at all points. So affine functions would certainly satisfy this. CPA satisfy this, but many more functions do too. And if there's a measure mu, which I'll call the Laplacian, satisfying that mass formula. So somehow that formula that I gave on certain kinds of sets is supposed to extend to a measure. And really is just a bounded, part 3 is just a boundedness requirement. This has to be a bounded measure. So I'm telling you the masses of all these pieces, and they're not supposed to go off to infinity. Those things showing up in the mass formula should stay bounded in order for this to extend to a measure. So this is just some definition, but in fact, this is a much larger class of functions than just the continuous piecewise affine ones. So for example, any function which is C2, twice continuously differentiable piecewise, and whose derivative is in L1 of gamma will be in BDV. There's and that. So you can allow functions that are sort of arbitrarily twice differentiable with some boundedness condition. So it's much more general than just the affine ones. Now, as I said, since the connected open sets generate the topology, this measure delta of f, if it exists, it's going to be unique. And by construction, it contains the piecewise affine functions. And in some precise sense, this is the largest class of continuous functions on which you can define a measure-valued Laplacian. And what I mean by that is you have this theorem. If nu is a measure of total mass 0, the Laplacian also always has total mass 0 from the mass formula. That's immediate, actually, because there's no boundary points for the whole graph. So that sum was empty. So you get 0. If nu is a measure of total mass 0 on a metrized graph, there is a function in BDV which is unique up to adding a constant whose Laplacian is nu. Right? So given f in BDV, you can take its Laplacian, you'll get a measure of mass 0, and you can go backwards. Any measure of mass 0, you can find a function f which solves this differential equation, and it's unique up to adding a constant. So this is a natural, so these functions in BDV modulo constants correspond to measures of mass 0. So that's why the definition is natural. And so that's what I just said. There's a natural bijection between measures of total mass 0 and functions in BDV. So these are just all things that you want to throw in, all kinds of functions that should be solutions to the equation Laplacian f equals any given measure of mass 0. Okay, so all those properties I gave just for affine functions, which was just some kind of linear algebra, actually extend to all functions in BDV. So all those properties still work. Laplacian is 0 if and only if f is constant. Laplacians of two functions agree if and only if they differ by a constant. This one is interesting. If for a non-constant function f achieves its maximum at a point in the support of the positive part of the measure. In the Jordan decomposition, you look at just the positive part, and the support of that is where you can achieve a maximum, and the support of the negative part is where you can achieve a minimum. So this is sort of a nice generalization of this maximum modulus principle. It's still self-adjoint. It's not completely obvious from the definitions that this still works, but it's true, and it still has total mass 0. And the crucial thing for the point of passing to inverse limits and doing things on Berkovich space rather than finite graphs is some kind of coherence property. Right? I should be able to compute Laplacian on a smaller graph or on a big graph, and they should somehow be related if I want to glue these things together to get an operator on this big inverse limit space. So here's the crucial property. If gamma and gamma prime are metrized graphs with gamma contained in gamma prime, and I think of gamma prime as just adding tree-like parts to gamma, so there's some kind of deformation retraction from the bigger graph onto the smaller graph. So this would be automatic if you have just one real tree contained in another. And if f is in this nice class of functions on gamma prime, then you have this formula. So what does this say? It says that you can first restrict f to the smaller graph gamma and compute its Laplacian there, or you can compute the Laplacian on the bigger graph gamma prime and then push forward under this retraction map. And those are the same. And so again, this is just from the definition of the Laplacian, you can check that this works. But this is the crucial property needed to glue these things together. So, and concretely, this condition that you have a deformation retraction from gamma prime onto gamma is really just saying that you get gamma prime by attaching finitely many R trees. And then you're just crushing those R trees down to a point in this map R. So it's, this will lead us to this notion of an arboretum. All right, so for an arboretum, I need to talk about inverse limits. So let me just recall a directed set is where you have some relation that's, what is that called? Symmetric, no, yeah, symmetric and transitive. And given any two elements, there's a third element that dominates both of them. So We just saw this with Raynaud's formal models, but this is a bit simpler here. So an arboreal system of metrized graphs is a directed set together with the following data. So for each element of my directed set, I give you a graph. And whenever I have alpha less than or equal to beta, then I should have an inclusion map of gamma alpha into gamma beta. And I should also have a deformation retraction from gamma beta onto gamma alpha. So you just think of, I have this system of graphs, and the gamma alphas are contained in the gamma betas when beta is greater than or equal to alpha, but also there's a retraction map going the other direction. This is exactly what we have with this Berkovich projective line. And so the arboretum attached to this arboreal system of metrized graphs is the inverse limit space taken with respect to these retraction maps. And this is what I was saying, that the Berkovich projective line is homeomorphic to such an inverse limit. It exactly has this kind of structure. But in fact, any Berkovich curve, well, smooth, I'm talking about the proper case, so sort of smooth, proper algebraic curve has this structure. But I'll talk about that in the last lecture. So anyway, a point of the inverse limit is a compatible system under these retraction maps. The inverse limit comes equipped with maps from the whole space onto each gamma alpha. And the topology is the weakest one that makes all these maps R alpha continuous. So properties of arboreta. First of all, an arboretum is a compact Hausdorff path-connected topological space. And there's a natural retraction map from the whole arboretum onto each gamma alpha. And the homotopy type for the whole space is the same. So intuitively, we have a family of trees that are like real trees sprouting from some finite metrized graph. Exactly as in the picture of the Tate elliptic curve that I showed before. So examples, the Berkovich projective line is an arboretum with respect to the system of all finite subgraphs, which I mentioned last time. Any smooth proper curve over K, its associated Berkovich analytic space is an arboretum. With respect to what? Well, you have the sort of dual graphs of all proper semi-stable models for X over the valuation ring of K. But this remark will be explained in lecture 5. So I'll tell you how to think about this in more detail next time. M of Z is an arboretum, the Berkovich space associated to Z, as I explained. And if you have any domain U, its closure is an arboretum. So what is the inverse system? Just take all finite subgraphs which are contained in U, and it's an exercise to show that U bar is just this inverse limit. So we can actually apply this not just to the whole space itself, but to the closure of any domain. And this will allow us to define the Laplacian not just on a whole space, but locally on any domain as a measure supported on the closure of U. Okay, so now to get a global Laplacian, we should just define coherent systems of measures. So if I have an arboretum, this inverse system of metrized graphs, then a system of measures is called coherent if when you have measures on each graph, and when you push forward under this retraction map, the measure on the big graph, you should get the measure on the smaller graph. And some boundedness property, so that these things will actually give us a bounded measure in the limit. So there should be some constant, so that the total mass of mu gamma is bounded by B. Remember, well, mu gamma has mass 0, but I'm taking the absolute value here. So the positive and negative parts should be staying bounded. And this is part of this bounded differential variation idea. So if mu is a measure on X, then it's sort of automatic that when you push forward all to each gamma, you get a coherent system. So if I started with a measure on the big space, I could get a coherent system just by pushing forward. But conversely, using the Riesz representation theorem, every system, coherent system, actually gives you a measure on the big space. So in other words, if you have a coherent system of measures on X, there's a unique measure mu on the big space X whose push forward to each finite graph gamma is the given thing mu gamma. So just a measure on the inverse limit space is just a coherent system of measures on each finite subgraph, which is not surprising. But it's useful because now we can define a space of functions on which we'll have a Laplacian. So BdV of x is now this big inverse limit space. I define BdV of gamma. BdV of x will be all functions. They're allowed to be plus or minus infinity, whose restriction to each finite subgraph is in BdV. So we can take the Laplacian of its restriction to any finite subgraph. And these measures these Laplacians on each finite subgraph have uniformly bounded total mass. So just a note, being in this space BdV says nothing about the values outside of this hyperbolic space associated to the arboretum, sort of analog of the complement of the points of type 1 and 4, actually, in this case. But somehow the points out at the boundary, we're just restricting to finite subgraphs, and those all lie in the P1 case inside the points of type 2 or 3. So we're not saying anything about the values there. Brian?
So you're not saying values plus minus infinity all hyperbolic?
Right, because BdV of gamma, those were real valued functions. Right, so the plus minus infinity are just at points of infinitely far away. But if you wanted to sort of deduce some kind of maximum modulus principle or something where you talked about the values at all points of x, then you'd have to impose some auxiliary conditions, like say that f was continuous on the whole space or something. So now, using the coherence property, you see that if f is in BdV of x, the space I just defined, then this system, you just restrict f to each subgraph gamma, you compute its Laplacian there, and those, by the coherence property, those form a coherent system. And so there is a unique measure, which I'll write delta sub x of f, of total mass 0, called the Laplacian of f, on this inverse limit space, whose push forward to any finite subgraph gamma is just the Laplacian of f computed on gamma. All right, so I will give some examples very shortly. But I mean, somehow this should seem like a natural construction. Whenever you have this kind of inverse limit space, you can do it. Okay, but it probably seems very abstract, so I want to tell you how to visualize this operator delta x. So how do you visualize it? Well, there's a very concrete way to visualize delta x. This is thanks to Xander Faber, who's here. Xander, there you are. This is on the campus here, actually. This is University of Arizona Delta Chi sorority house. And sorry, I don't actually have a better way of visualizing the Laplacian operator. That's the best I can do. But I will give you some examples. So, for example, take the function f on the Berkovich projective line, which is minus log of this canonical distance. So remember, this canonical distance was the Berkovich space extension of just the absolute value of x minus y. And so what is the Laplacian of this thing? So this is an example of a function in BdV. In fact, it's piecewise affine. And its Laplacian is a discrete measure. You have a point mass at y minus a point mass at infinity. And somehow this is coming from the fact that all this function is doing is it is increasing on the path from y to infinity. And so at y you have sort of, oh sorry, did I say that back? I think I said that. Yeah, I said that backwards. So at y, you have the minus log of the distance from y to y. So if y is a type 1 point, say, that's plus infinity. This function would be plus infinity there. And at infinity, it's going to be minus infinity. So you have sort of singularities at y and at infinity if y is a type 1 point. And the function is just linear with slope 1 along that path, going from plus infinity down to minus infinity with slope, I guess, minus 1. And then it's locally constant off of that path. And so the Laplacian is just picking up where you have some kind of change in slopes. And so where you have them is at these two endpoints. And everywhere else, it's locally constant, so there's no change in slope at all. And somehow this whole formalism of taking these inverse limits and doing all this stuff I spent the first half of the lecture with is just to get around these infinities. I mean, you have all these, this metric is singular along the boundary, so it's better to compute it at finite levels and pass to the limit rather than to try to make sense of taking derivatives at points which are infinitely far away, right? So it's just some neat formalism that gets around this problem of infinities. But intuitively, you just have a segment, and the function is linear with slope 1 along that segment, and it's constant everywhere else. So you should just get kind of a point mass at one endpoint minus a point mass at the other endpoint. And to check this, by the way, you just have to check that this is correct when you restrict to any finite subgraph, and then compute the Laplacian there, which is easy. So the uniqueness property, it's characterized by a property that shows that to check such a formula, you just have to check the restriction to any finite subgraph where it becomes an easy computation. And so anyway, this shows that this function, like its classical counterpart, minus log absolute value x minus y, sort of gives you a fundamental solution of the Laplace equation. This, roughly speaking, allows you to, using this as an integral kernel, allows you to invert the Laplacian operator. So if you want to solve differential equations, Laplacian equals something, you integrate against a certain kernel. And this is the correct thing to use because of this property. So this is, I mean, if you know the classical point of view that I'm describing, then that will make sense. And otherwise, it probably won't. But this function shows up all over potential theory. This is where potential theory, the name comes from, right? Because in physics, this is some kind of potential function. So anyway, this is kind of the main type of function that you use in complex potential theory, and its counterpart in Berkovich space is this guy. So that's why I wanted to define that canonical distance before. And another example, I defined this funny Gromov product. I'm not going to recall the definition now, but it is also piecewise affine and satisfies a similar differential equation. Its Laplacian is delta y minus delta z. But if you've forgotten the definition, then go back and look at the notes. So I want to tell you the relationship with the harmonic functions. So here's the relationship. If you have a domain U, U bar is an arboretum, as I mentioned, and so there's a Laplacian on U bar. And the relation between these two concepts is just the following. If U is a domain and F is in the space BdV, then F is harmonic if and only if its Laplacian is supported on the boundary of V for every simple subdomain V. So, in fact, you can work sort of on more general domain. I mean, you get something stronger. It's not just true for simple subdomains, but for all subdomains. But somehow on the simple subdomains, we have a very concrete formula for what it means to be harmonic. And so this is a nice concrete way to relate harmonic functions to the Laplacian. So the idea is that the Laplacian is always a measure supported on the closure of the domain. And you'll be harmonic on U if there's no mass on the interior. All the mass gets pushed out to the boundary. So this nicely this sort of tells us that we have a good notion of a Laplacian and a good notion of harmonic functions because these things are compatible. And similarly, if I have a domain and I have a continuous extended real-valued function that's maybe now allowed to be minus infinity at some places, then it's subharmonic if and only if the Laplacian is a negative measure for every simple subdomain. And remember, I sort of said you have this maximum modulus principle. The Laplacian is negative where you can, well, anyway, so this is related to the maximum modulus principle. And what I really wanted to point out is that I wrote continuous here, but subharmonic functions need not be continuous. So this isn't quite an if and only if condition, but you can exactly characterize subharmonic functions in terms of this condition, but there's some auxiliary things that I don't want to discuss about semi-continuity that you have to say. So there's this nice formula, which I'll just state for rational functions now, but I'll talk about some generalizations next time. If you have a non-zero rational function, then, and its divisor is div phi, then, as I mentioned, the usual action of phi on the projective line extends naturally to an action on Berkovich space. And I can talk about this function minus log absolute value phi. There's a unique function that extends this map on points. And the Poincaré-Lalonde formula in this context would say that when you take the Laplacian of minus log absolute value phi, you just get point masses at the zeros and poles with the right multiplicities. So you can actually recover the divisor of a function by taking the Laplacian. And what you're supposed to think of here is that outside the zeros and poles, this function is harmonic, so the Laplacian is 0. So the only place where you're going to have mass is at the zeros and poles. And what are the multiplicities? They're exactly the order of the zero or pole, is getting picked up by this Laplacian. So what I want to do in the last part of the talk then is to interpret this formula. So the claim is that, and by the way, there's a classical analog of this, which is why it has a name that has nothing to do with Berkovich spaces. But I want to give you, I claim that this somehow is a known fact from p-adic analysis. This has some definite meaning, and I want to give some examples that show what this actually means and how it's related to, say, Newton polygons. Okay, so first of all, what this formula tells you is that if you have any Borel set A, then when you take the mass of this measure, this Laplacian measure, the mass on a set A is the number of zeros in A minus the number of poles in A. That's just that's an exact translation of the previous formula. So this Laplacian is counting the number of zeros minus the number of poles in a set A with multiplicities. But remember, how do we define the Laplacian in the first place? It was some kind of sum of directional derivatives, right? So we're saying that we can count the number of zeros minus the number of poles of some rational map in terms of certain directional derivatives. So that's not an obvious statement, right? And this is where this p-adic analysis comes in. So this is a thing you'll find in Robert's book, for example, A Course in P-adic Analysis. You'll find, of course, stated completely differently, but you'll find an equivalent formula, and let me explain how it's equivalent now. So V is a simple domain with finitely many boundary points and finitely many ends. There was the picture again. I'm just going to talk about simple domains where we have finitely many boundary points. Otherwise, that previous formula is sort of too complicated. But I'll tell you what it says for simple domains. So by the mass formula, right, we said that the Laplacian satisfied this mass formula. So what we get is that the number of zeros of phi in V minus the number of poles of phi in V is some kind of sum over of certain directional derivatives. What are we taking derivatives of? We have minus log absolute value phi just at these boundary points xi and in the direction vi of this end. So we have the simple domain. We have these finitely many tangent directions. We're taking the derivatives of this function in those directions, adding them up, and the claim is that's the number of zeros minus the number of poles. So here's a concrete example of this. Oh, so this is basically what's called the theory of valuation polygons. There's some kind of, well, anyway, I prefer to say it this way for this talk, but you can say it without Berkovich spaces by constructing some kind of valuation polygon, which is sort of dual to the Newton polygon. But here's an example that should make this clear. Take the polynomial t squared minus t and look at this function. By the way, I'm writing minus log all the time. That's just a valuation, right? So in Teitelbaum's talk, for example, he's using additive valuations. Kieran was using this too. So when I write minus log sub v absolute value, I'm just looking at valuations rather than absolute values. But but if you want to do analogies with complex numbers, it's better to write things this way, because you don't somehow have the valuations over C. You have the absolute values naturally occurring. Anyway, so if I look at the open unit disk, which I'll call D, and V, it has one boundary point, right, in the same sense as in Brian's last talk, and there's one tangent direction going inward, then this function is linear with slope 1 along the path from the Gauss point to 0. Remember, this is just the soup norm. If x corresponds to a disk, it's just the soup norm along that disk, and so we're just measuring the change in the soup norm along some path. And so this directional derivative at the Gauss point is 1, because going down towards 0, this function has slope 1. And indeed, the number of zeros in the open unit disk of t squared minus t is 1. And so this corresponds to the derivative at the Gauss point. So the derivative of this function at the Gauss point is measuring the number of zeros. And similarly, you can do this. You could look at the number of zeros in the closed unit disk. And then, because of this mass formula, everything gets reversed. So you look at the opposite tangent vector. You look at the tangent vector pointing from the Gauss point towards infinity. And then what you find is that in that direction, actually, the derivative is minus 2. Sort of previously, this term dominated, but now this term is dominating, depending on which direction you're moving in. And so now this derivative is 2, and now, indeed, in the closed unit disk, we pick up an extra 0 of this function. So this is a neat way of encoding this classical theory. And so finally, just to conclude in 90 seconds, I want to say how this works on M of Z, because it's very cute. So we have a Laplacian on M of Z as well, from what I've said, because of this arboretum structure. And what it means very concretely is just this. You'll recall that minus log absolute value n, where n is just some non-zero integer, is linear with slope equal to minus log absolute value n with respect to the v-adic absolute value on that branch. And so we said it was harmonic at the Gauss point by the product formula. But the Laplacian, so if you compute it, you get a sum of point masses where you're just recording log absolute value n at the endpoints of that tree. So at the finite places, you have a point mass at that p-trivial semi-norm, and then at the infinite place, you have the corresponding opposite point mass. So, for example, if n is 12, what is the Laplacian of minus log absolute value 12? It's log 4 times at this point. It's log 3 times at this point, and minus log 12 at the Archimedean point. So colloquially, the Laplacian is factoring n. And that's what it's doing, is factoring n. And even better, I could take not just analytic functions like n, but meromorphic functions like m over n, right? So I think of a rational number as a meromorphic function. And if I compute the Laplacian and I take its Jordan decomposition, then I claim this is the mass of the positive part is the V height of the rational number. So here's an example. If alpha is 4/3, the Laplacian of this function is log 4 times this point minus log 3 times that point and minus log 4/3 at infinity. And so the positive and negative parts both have mass log 4, which is the height. It's the maximum of the numerator and denominator written in lowest terms. And the project I gave, one of the projects my group will do is generalizing this to Q bar. So in fact, this should work for Q bar as well, that you can have a Laplacian on the Berkovich space associated to Z bar, and that is just computing the V height of an algebraic number. So I'll stop there. Thanks. That's correct. I actually removed that slide because I knew I was going to run out of time, but I originally was going to explain that. So the question was, isn't it really sort of a second derivative operator away from these branch points? And yes, it is. So if you have a function in BDV which is twice continuously differentiable along the edges, piecewise, then the Laplacian is actually much more concrete than what I said with this abstract mass formula. It's just the combinatorial Laplacian at the branch points giving you certain point masses, and then along the interiors of edges, it's minus the second derivative of the function. So it's minus f double prime of x dx. And this actually is Xiao Zhang as a paper where he uses this kind of stuff in the setting of Arakelov theory, and that's sort of his definition is you take this minus f double prime of x dx plus this combinatorial Laplacian at the branch points. And the description I gave is sort of more general than that, in that you don't require twice differentiability.